Hello, my name is Nandini. Today I am going to discuss about divide and conquer sequential matrices, diagonalization for para-Hermitian matrix. Introduction. Polynomial matrix formulation can be used to express broadband multi-channel problems. Examples include broadband MINOMO, precoding and equalization, polyphase analysis and synthesis matrices for filter bands and broadband beamforming. Typical these problems involve para-Hermitian polynomial matrices, which are identical to their para-Hermitian conjugate, that is R of Z equals to R bar Z equals to RH of 1 by Z star. Matrix of R of Z can arise as the Z transform of a space-time covariance matrix of R of T. A polynomial matrix eigenvalue composition has been defined as an extension of the eigenvalue decomposition to para-Hermitian polynomial matrices. The PEVD uses the infinite impulse response para-unitary matrices to approximately diagonalize and spectrally majorize a space-time covariance matrix. Existing PEVD algorithms include the second-order sequential best rotation algorithm, sequential matrix diagonalization, and various evolution of the algorithm families. Each of these algorithms use an interactive approach to approximately diagonalize a para-Hermitian matrix. Efforts to reduce the cost of PEVD algorithms include techniques for the trimming of polynomial matrices to curb growth in order, which translates directly into a growth of computational complexity and memory storage requirements. Recently, techniques in have successfully reduced the complexity of existing PEVD algorithms through the removal of algorithmic redundancy. Research has demonstrated that complexity reduction can be obtained by using a divide and conquer approach to eigenproblems. Inspired by these works, here we describe a divide and conquer approach for the PEVD, which can be utilized to reduce algorithm complexity with minimal loss in accuracy. The framework of the developed algorithm titled Divide and Conquer Sequential Matrix Diagonalization is based on the SMD algorithm. Below section, I will provide a brief overview over SMD algorithm. The proposed divide and conquer approach to sequential matrix diagonalization. The SMD algorithm approximates the PEVD using a series of elementary para-unitary operations to interactively diagonalize a para-Hermitian matrix R of Z its associated coefficient matrix. Upon unitalization, the algorithm diagonalizes the lag zero coefficient matrix R of Z by means of its model matrix obtained from the EVD of the lag zero lines R of 0 is applied to all coefficient matrices. and intelligence algorithm computes the product. The product team consists of a para-unitary delay matrix and a unitary matrix with the result that is para-unitary for subsequent discussion. It is convenient to define intermediate variables S. Presents the element in the mathro and mnth row and kth column of the coefficient matrix at large. The shifting process moves the dominant of diagonal row and column into the zero and coefficient matrices S. The off-diagonal energy in the shifted row and column is then transferred onto the diagonal by the unitary matrix, which diagonalizes by the means of offered EVD. Interaction continues for one step until S of I is sufficiently diagonalized with the dominant of diagonal column north, where the value of Q is chosen to be arbitrarily small. On completion SMD generates an approximate PEVD given by truncation of outer coefficients of H of I of Z with the small Frobenius form is used to growth in order, whereby the maximum and minimum lags. In interaction, iteration I are reduced from respectively such as truncation of S of I of Z is similar with its maximum and minimum lags reduced from I3. At the ith iteration, the length of computes the length of a polynomial matrix. Every matrix value coefficient in S must be left and right multiplied with a unitary matrix, accounting for a multiplication of 2m into m matrices by M3 max a total of 12 S. Max arises to generate every matrix value coefficient in must also be left multiplied with a unitary matrix. Thus, a total of max arises to generate that the cumulative complexity of the SMD algorithm over iteration can therefore be approximated as divide and conquer sequential matrix diagonalization. The DC SMD algorithm diagonalizes a para-Hermitian matrix R of Z via a number of para-unitary operations. An output diagonal matrix D of Z contains the eigenvalues and F of Z contains the corresponding eigenvectors. While the SMD algorithm attempts to diagonalize an entire M into M para-Hermitian matrix. It once the DC-SMD algorithm first divides the matrix into a number of smaller independent para-Hermitian matrices before diagonalizing or conquering each matrices separately. For example, a matrix of Z might, might be divided into 5 into 5 para-Hermitian matrices, each of which can be diagonalized independently. If matrix R of Z is of large spatial dimension, an algorithm named sequential matrices segmentation (SMS) is used to recursively divide the matrix into multiple sequential matrix segmentation (SMS) is used to recursively divide the matrix into multiple independent para-Hermitian matrices. Each of these is stored on the diagonal of matrix R of Z. Thus, R Z is block diagonal by construction. The matrix T of Z, which SMS generates to divide each R of Z, are concatenated to form an overall dividing matrices G of Z. It is therefore possible to approximately reconstruct R of Z from the product Z of Z, R of Z, Z of Z. Each block on the diagonal of matrix R of Z then diagonalized in sequence through the use of the SMD algorithm. The diagonalized outputs D of Z are placed on the diagonal of matrix D of Z and the corresponding para-unitary matrices S of Z are restored on the diagonal of extension. It is possible to approximately reconstruct R of Z from the product Z bar of Z, H bar of Z, D of Z, H of Z, G of Z equals to F bar of Z, D of Z, F of Z. Algorithm 1 summarizes the above steps of DC. SMD is more detailed of the parameters input to DC SMD. Mu is a truncation parameter and Q is the previously mentioned stopping threshold for SMD. Matrices of spatial dimension greater than M bar into M bar will be subject to DC SMD parameters P, gamma, ID, and IC will be discussed in subsequent sections. Matrices IM into M and OM into M are identity or zero matrices of spatial dimensions M into M respectively. Diagonalization. The ensemble averaged diagonalization was calculated for both The standard and proposed implementation, the diagonalization performs passes time and cumulative complexity for both methods are respectively. The curves of demonstrate that for any the proposed implementation operates with a lower cumulative complexity than the standard assembly realization and is able to achieve a similar degree of diagonalization. The standard assembly realization line is able to achieve a similar degree of diagonalization. The lower complexity associated with the DC and assembly translates to a faster diagonalization than observed for assembly using a matrix with a large spatial dimension of m equals to 40 demonstrates a large increase in diagonalization performance with respect to execution time. In both plots is the expectation operator. The stepped characteristics of the curves for DC SMD are a result of the algorithms. Accuracy two-stage implementation, the divide step of the algorithm, exhibits how diagonalization for a large increase is cumulative complexity and execution time. In the concourse step, high diagonalization is seen by a small increase in cumulative complexity and execution time. This is the polynomial eigenvalue decomposition. PEVD for a para-Hermitian matrices and orthonormal eigenvectors and along each Hermitian matrix can be diagonalized by an unitary matrix. Diagonalization of a PH matrix. Conclusion. We have proposed an alternative technique to compute the polynomial EVD of a para-Hermitian matrix. This algorithm named DC-SMD makes use of a divide and conquer approach to the PEVD and has been shown to operate with lower computational complexity than the traditional SMD algorithm. Simulation results have demonstrated that this complexity reduction and the associated execution time decrease come with the disadvantages of increasing the mean squared reconstruction error and para-unitary filter order. When designing PEVD implementation for real applications, the potential for the proposed techniques to increase diagonalization performance while reducing complexity requirements offers benefits. A further advantage of the DCSMD algorithm in its ability to produce multiple independent para-Hermitian matrices which may be processed in parallel. Thank you, ma'am.